Space project number 2 with flow over a flat plate. We're going to start by putting our Fluent block on our workbench, and we're going to start by creating our geometry, which in our case is just going to be a rectangle, and we're going to change our boundary conditions to go ahead and set the simulation up. But for now, we're just gonna make our shape here. Excuse me. Our length is going to be 1 meter. And our, that's the height. We're going to make this 1/2 meter and make our length 1 meter. Excuse me. Oh, this is the wrong way. Let's change this. Alright, and now that that's done, we're gonna create a surface from our sketch. And go ahead and generate that. And once that's generated, we can move on to our mesh. I'm sorry, I'm pretty sick, as you can hear, but I needed to finish this project as soon as I was able to, so here I am. Alright, once your mesh is up, soon, I'm going to go ahead and change the orientation of it, and we're going to first create our name selections. Doesn't really matter what you call this, you can just name it that. Far field. This bottom one, however, is important. This is going to be our flat plate. This is always going to be our inlet, and right here our outlet. Now can name excuse me, this as well. This is going to be our airflow. And after we're done naming that, we're going to start our meshes. We're going to start with a face mesh with our airflow selection and generate that. Once that's done, you're going to see it's very coarse, so we're going to need to insert other meshes. Select the edge at the top and the bottom, apply that. I'm going to change this from element size to number of divisions and make it about 50 divisions. We do not want any curvature, and we want to make this behavior hard. And generate. Once that's done, you're going to see here it's still pretty coarse, but we're going to want to find mesh at the bottom near our plate so we can get accurate readings. So to do that, we're gonna make a biased mesh, making these sides coarse and getting finer and finer as you go down towards the plate. Excuse me. Same thing here. Now you're gonna add bias. We want this type of bias, decreasing in size. Our bias factor is gonna be 70, and since we see the preview here, that's exactly what we want. So we're gonna go ahead and generate that, and you're gonna see that it's skewed here, and we want both sides to be the same, so we're gonna do the exact same thing we did to the inlet to the outlet by inserting the same exact type of mesh. It's all the same things except for the end here that I'm about to show you. Now you're gonna want bias, but the bias factor will be the same, but you'll see here, oh, I didn't select the number of divisions. You'll see here that it's upside down, so all you're gonna have to do is select the edge that you're gonna want to flip and apply it to reverse the bias, and then you can see here that it's the same as the left side, the inlet. And then you go back and you see your mesh is just as you want it. So we're gonna go ahead and exit our mesh and move on to the setup portion, where we will excuse me, where we will input our givens. Alright, once your setup has loaded in, you're going to go ahead and make sure that your model is a laminar model. Hit OK. We're going to go down the list here, and everything under here looks fine. We're going to go to our material, and we're going to input our given constants, which was a density of 1.2 and a viscosity of 1.8 times 10 to the negative 5. And go ahead and change that. Then we're going to move down to our boundary conditions. Our inlet is going to have a velocity of about 2 meters per second. Apply that. Make sure I apply that. Okay. Excuse me. We're going to make sure excuse me, that our flow here is reversed. And we're going to go ahead and apply that and close it at our outlet, our flat plate. We're going to make sure that it has a no slip condition and that it is stationary, because that's important for our simulation. And we're going to change this to a symmetry plane. And once that's done, we're going to check our reference frames. Everything looks good. And our reference values will be computed from the inlet. And make sure that everything here is right. Velocity is right. Density, everything. Check. Our methods. We can make this simple because we have a pretty basic geometry here. our residual, we want to make sure that it's 0, 1 times 10 to the negative 5 to make sure that we're getting our residuals below that. And when we initialize this, we're going to make it a standard initialization, computing it from the inlet, making sure our x velocity is 2, and go ahead and initialize that. Make sure that it's ready to be ran. And once we run this, we're going to make a lot of iterations, which our solution should converge before we get to this number. So it shouldn't take too long. And there we go. That was pretty quick. Now that we have ran our solution, we can plot from here our wall fluxes. This is how we will get our wall shear stress on the flat plate. We can see here what this plot will look like, and we can output this into a file which we can put in Excel to compare to our theoretical data, which is how we plot both theoretical and computed values on one plot in our report. And I will now show you the other thing we're looking for, which is the skin friction coefficient. So once we have that, we select the flat plate once again and plot it. And it looks similar, but it is different. And here it is. And that should be all for this. Oops, no, I forgot the force here. Excuse me. And this is going to be the force, or how we get our drag coefficient. You can see here it is 0.0039, which is very close to our theoretical one, which validates our data. Now we are going to go ahead and open up our solution, our results, which we'll be able to get our velocity profile, which is the last thing we need. Excuse me, which is the last thing we need for our video. So we're going to go ahead and get on the XY plane. Make your lines. You can call this one 35. I'm just kidding. We can't put in numbers. This will be line 1. Do 100 samples. Go ahead and apply it. We can have our line 2. 0.75. It's from 0 to 0.01. We can once again do 100 samples. go ahead and apply that, and then we can make our velocity profile where our excuse me, data series here. Our line 1 will be our 35 centimeter line, and our line 2 will be, oops, we gotta change our axes. And I think that might be too small. There we go. I just had to change the line. Yep, and that looks right for our velocity profiles. And I believe that is all. And from this, we can export our data into Excel to be able to find the values for the thickness of the boundary layer from here. That's pretty much it. Thank you to everyone who's watching this. Have a great day, and I'll see you guys